Hello everyone. Today we are going to discuss an important topic in biomedical image processing called Wiener filtering, which comes under image restoration. Image restoration is the process where we try to recover the original image from a degraded images. In biomedical applications, images like MRI, CT, and ultrasound are often affected by the noise or blur during acquisition. So our goal is to improve image quality in such a way that it becomes useful for diagnosis. In today's section, we will understand why image degradation happens, why simple method fail, and how Wiener filtering provides an optimal solution. By the end of this lecture, you will clearly understand both of this concept and its practical importance. Let us first recall the image degradation model. In real-world imaging systems, the captured images is not perfect. It is affected by the blur and noise. Mathematically, we represent this as original images passed through a system that introduces a blur and then noise is added. In spatial domain, this is represented using convolution. In frequency domain, it becomes the multiplication. Here, H of UV represent the blur and N of UV represent the noise. So the observed image is always a combination of both. The important point is restoration must deal with the both blood and noise simultaneously, not just one of them. Now let us understand why inverse filtering is not sufficient. Inverse filtering tries to remove the blur by dividing by the degradation function h of uv. But there is a serious problem when h of uv becomes very small or close to zero. The division causes huge amplification of noise. So instead of this improving the images, it introduces strong distortions. Also, inverse filtering becomes unstable in such conditions. So the main problem is we need a method that removes a blur but does not amplify the noise. The limitation leads us to a Wiener filtering. Wiener filtering is an advanced and optimal approach. It does not just remove blood blindly. Instead of it uses the degradation models, statistical information about the noise. Its main objective is to minimize the mean square error, which means minimizing the difference between the original and restored image. Because of this, it is also called minimum mean square filter, optimum linear filter, statistical filter. The key idea is balance that it removes the noise while preserving important details like edges. So Wiener filter is intelligent and adaptive. Here we can see the mathematical formula of this Wiener filtering. Here f of uv is the output image or the input image. Here h of uv is multiplied with the h of uv. Let us and now understand the simplified Wiener filter formula. This equation has two important parts. The first part is similar to inverse filtering, which attempts to remove blur. The second part is correction factor that controls the noise. Here, K represents the noise to signal ratio. Now we can observe the K is the small, the filter becomes like inverse filtering. The K is large, more smoothing happens. So the K plays a crucial role in balancing blur and removal of noise suppression. This is what makes Wiener filtering adaptive and stable. This slide explains how Wiener filter behaves in frequency domain. The filters does not treat all frequencies equally. High noise regions suppressed. Important signal regions are preserved. So instead of uniformly processing the image, it adapts based on the noise removal. That's why we call it adaptive filter. The key takeaway is Wiener filter intelligently decides what to keep and what to remove. This slide shows how the Wiener filter behaves in the frequency domain. The filter adapts its responses based on noise removal. For high noise frequencies, the filter suppresses them to reduce dissolution. For low frequencies, it processes them to maintain image details. So unlike fixed filters, Wiener filter dynamically adjusts its behavior. The key takeaway is it intelligently separates the useful signal from the unwanted noise. Let us now see how Wiener filter works step by step. First, it estimates the relationship between the signal and noise. Then, based on the estimation, it applies the controlled restoration. The final output has reduced noise, preserved edge, and fine details. So, instead of over smoothing or over sharpening, it provides balanced result. This makes Wiener filtering highly effective from the real world applications. In biomedical imaging, Wiener filtering plays a crucial role. In MRI, it reduces noise, improves clarity. And in ultrasound, it reduces speckle noise, which is very common. And overall, it helps in producing clear diagnostic images, which supports accurate diagnosis. So this is not just a theory, it has a real clinical importance. Let us summarize the entire concept using the minimum. Wiener filtering is based on the degradation model. It have a non-statics and it also called the mean square error filter, and it mainly works in the frequency domain. It has multiple names and wide range of applications. However, the one limitation is it requires prior knowledge of noise characteristics. The key idea of remember is effective restoration requires both blur and handling the noise control. Finally, it is the references and some of the reflective questions. Thank you.